Hi, I'm Carlo Mazzola, PhD student at the Italian Institute of Technology, and I'm going to show you how the interaction with a social robot can modify visual perception of space. Think about an interactive scenario. Humans are very good at coordinating with each other. Maybe not always, but a high level of coordination is required in music, dance, sports, or even in all those daily actions in which we collaborate with others, and we are quite good at performing them. Such successful coordination is all the more remarkable considering that people perceive the world each in their own way. For example, look at these two faces. Can you find any differences between them? The face on the right is concave, but you probably didn't notice that because we are all used to seeing only convex faces. This example shows us an important feature about perception. Perception is not the mere reception to external stimuli. It is rather an inferential process where our previous experience affects what we perceive. There is a sort of a priori in our perception. That's the reason why we can call such previous experiences priors. Now, there are some priors that remain constant during our life, like the convex faces, and others which change in time. For instance, it has already been demonstrated that perception of space is influenced by the stimuli perceived before, and that these priors change according to the stimuli you receive. If I show you two short segments, and then I show you a longer one, you will perceive this latter as shorter. Regression to the mean is the name of such phenomenon. Our brain works in this way to gain stability and optimize perception, in particular when stimuli are ambiguous. But how does this perceptual mechanism work during interaction? If when we are alone we use our previous experience, our priors, to optimize perception, what happens when we are with other agents, everybody with different experiences? How do we use priors for an optimal shared perception, and how much do we rely on them? And these questions are all the more relevant in case of interaction with robots, that for sure have a different perception from us. That's the reason why we tried to figure out the answer within a human-robot interaction experiment. We started from a well-known paradigm used to study regression to the mean in space perception. Participants performed the task using a touchscreen. Well, not in this way. They were shown different lengths on a screen, and they had to reproduce the presented lengths touching the screen at the correct point. But since the experiment was focused on performing this task with the robot, as you can see in this video, it was iCub that presented the stimuli to participants. The robot touched the screen in 2 points. Then, it was the participant's turn to reproduce the length. In particular, participants performed this task twice. Once with the robot behaving as a social agent. iCub looked at the participant and at the point it was touching as well. Also, its face was endowed with social patterns. It showed emotions and it moved its eyelids. In addition, it spoke to say hello to participants, to explain the task and to encourage them. On the contrary, in the mechanical condition, iCub didn't show any of these social skills. It just moved its arm. And here are the results. In all conditions, we assessed that all participants showed a certain degree of regression to the mean. Indeed, the plot of their responses revealed a shift from an ideal accurate reproduction. This shift is the regression index, which indicates how much we rely on our previous experience during perception. Our main question was if the influence of priors changed within a social interactive context, and our results revealed that in the social condition the regression index is significantly lower than in the mechanical one. In other words, interacting with the social agent, we rely markedly less on our previous experience. If so, what does this interactive mechanism optimize? Is it in order to stay more focused on the current stimulus or for something else? This paves the way for further research, which we are already carrying out. But from the data we gathered from the Godbit questionnaire, we noticed that the more the robot was perceived as anthropomorphic, the more participants changed their perception of space, relying less on their previous experience and more on the current stimulus. To sum up, this study points out that when we consider perception of space, we have to take into account that interaction is a key factor in perceptual processes, enough to modify what we perceive. Interaction modifies the weight of our previous experience in perception. In other words, when we are interacting with someone else, our brain changes the very mechanism that we use to perceive space. Why is this relevant for robotics? Robots can be equipped with the most performant sensors, cameras and microphones, so why endow them with the human perceptual distortions? Because a perfect perception might not be enough for the purpose of interaction. Awareness of human perceptual processes could indeed improve HRI at least in 3 domains. Firstly, it could lead robots to predict and accordingly to enhance their adaptive perception in joint actions. Next, robots could help humans and correct this misperception in case the phenomenon of the regression to the mean does not elicit optimality. Above all, in rehabilitation contexts, robots endowed with such ability could compensate and improve human performance. There are other 2 important takeaways. Cognitive science and HRI studies can stipulate a mutual advantage, and our study can demonstrate it clearly. First, robots can really boost cognitive science research by ensuring real interactive scenarios with an embodied agent for experiments. Vice versa, our results might be helpful for HRI studies, giving a new quantitative method to measure the level of interaction between users and robots. Here, you can find a link to the research project to find out what we do, and more importantly, the link to read the paper. Thank you.